Whoa, 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 whoa. Oh. So hello, welcome to the Beyond IoT 4.0 workshop 8.5. I'm Manuel Caballero of Nimbus Research Center at NTU, and I will be moderating this workshop. The title of this workshop is Applied Artificial Intelligence. We have two wonderful speakers today with us who will tell us all the info we need regarding this topic. The format of this workshop will be a slideshow followed by a Q&A session. Please take part throughout the workshop by typing your questions into the chat area, and the speakers will answer those questions at the end of the workshop. Please note that this workshop will be recorded. And now it's time to get fun. I'm pleased to welcome our next speaker. First one, Mr. Dr. Connor Lynch. Hi, Connor. How are you doing?
Hello. Can you hear me? Yeah.
I can hear you. Yeah. So while you are getting ready, I'm going to introduce you to our audience.
Okay.
So Dr. Connor Lynch is a senior research engineer here at Nimbus Research Center. Connor was awarded the Irish Research Council for Science, Engineering and Technology Enterprise Partnership PhD Scholarship. Partnering with United Technologies Research Center, he concluded his PhD degree in model predictive control, focusing on Kalman filtering optimization techniques to optimally schedule the renewable energy contribution within a microgrid in the process. Energy and Transportation Department at Cork Institute of Technology in 2016. Now he leads the AI, machine learning, and data analytics team within Nimbus. So did I miss something?
No, I think that's it. Thanks for the kind introduction.
So are you ready?
So I just kill the video there, that's the saving bandwidth, and we can turn it on again at the end for the questions. Okay. So welcome everyone to the workshop session on applied artificial intelligence. Today I'll try and walk you through some of the terminology around artificial intelligence, or AI as it's more commonly known, and we'll touch on the differences, I suppose, between AI, deep learning and machine learning. And I'll try and introduce you to, I suppose, some of the applications, or show you the more importantly, the potential for these tools. And finally, we'll go through some of the real world examples from our own in-house projects within Nimbus, and demonstrate, I suppose, to all of you here, I suppose, how these tools are kind of augmenting and assisting today's commercial environment from a real world perspective. I'm going to go on to the next slide. Okay, so I suppose to begin with, we might ask ourselves, I suppose, what is AI? And the term AI, I suppose, often gets confused, I suppose, and we just go back to the heart of it. I suppose it was originally coined, I suppose, in the 1950s by Dr. John McCarthy, whose father, I suppose, was an Irish immigrant from Kerry. So from an Irish point of view, we can claim some, I suppose, credit for AI. And John McCarthy was based in the University of Stanford and was one of the founders of the discipline AI itself. The goal of AI then, as it is now, was to get computers to perform, I suppose, tasks regarded as uniquely human, i.e. things that require some form of intelligence to complete. Initially, I suppose, the early research in this domain worked on problems like the games such as chess or checkers, and solving logic-based problems like if and else. And however, today, I suppose, we see AI and machine learning applied to myriad of domains, and including applications to vision perception or AI vision problems, such as number plate recognition systems. We see it being used for speech recognition or natural language processing, or NLP, as it's more commonly known today. We see it being used in the various chatbots. We also see it being used for, I suppose, the decision-making processes based on a series of one or more inputs, or a single input, single output, or multiple input, multiple output systems. And we also see it being used, I suppose, in anomaly detection, which often, I suppose, feeds into preventive maintenance systems. I suppose we'll now, I suppose, touch on these in greater detail. And so, I suppose before we go further, we've now said what AI is, and the next, I suppose, part of that is to kind of say what machine learning is. And you might well ask, what is machine learning? Or more importantly, I suppose, what's the difference between the two? Because I suppose they're almost used interchangeably by a lot of people. So now the reason for that, those earlier researchers I mentioned earlier found some problems to be much harder, like the checkers and the chess, is that those problems simply weren't amenable to, I suppose, early techniques used in AI. So hard-coded algorithms or fixed rule-based systems, although suitable for problems like playing checkers or chess, just didn't work very well for things like image recognition or extracting meaning from text or other data forms. So the solution to this problem didn't turn out not to just be mimicking human behavior, but i.e. AI, but we had to mimic how humans learn, i.e. machine learning. So we needed to mimic the process of gaining knowledge or skill by studying, so to speak, i.e. to simulate how we're taught or how we experience something. So yes, the answer is yes, machines can learn and do so by studying data to detect patterns or by applying known rules. For example, to categorize or catalog like people or like things, or to predict likely outcomes or actions based on identified patterns. So equally, these algorithms can be used to identify, I suppose, unknown patterns or relationships, or detect anomalous or unexpected behaviors. So with the advent of big data or data lakes that we see today, both the amount of data available and our ability to process it has increased exponentially, especially with augmented computational power. So the ability of machines to learn and to appear even more intelligent has increased proportionally. So the process machines use to learn is known as algorithms. So that's what we mean when we use the term algorithm. So as we will see more detail as we go on through the presentation, different algorithms learn in different ways. As new data regarding observed responses or changes to the environment are provided to the machine or the algorithm's performance improves, thereby resulting in increased in intelligence or appeared intelligence over time. So I suppose in summary, before we get in a little bit deeper, AI means getting a computer to mimic human behavior in some way, and machine learning is a subset of AI and consists of the techniques that enable computers to learn and figure things out from data to deliver AI applications. And to expand even further, we see another more commonly used term, deep learning. And this is a subset of machine learning that enables computers to solve more complex problems by employing even more or larger data sets. So from an overview point of view, there's essentially 4 types of categories of machine learning algorithms. So they're supervised learning, unsupervised learning, semi-supervised learning, which is obviously more, as you might guess, is a blend of the 2 aforementioned techniques. And then we have reinforced learning. So let's take the first one of those, supervised learning. So in supervised learning, the machine is taught by example. So i.e. examples of the desired inputs and outputs are provided. So the machine, aka the algorithm, uses this input to determine correlations and logic that can be used then to predict the answer or the output that we want or the desired response. So essentially, from a child's point of view, it's spoon-fed. So it's a spoon-fed version of machine learning. So i.e. you select what kind of information or inputs or samples to feed the algorithm, and you, the data scientist in this case, determine what kind of results are desired. So from the machine's point of view, this process is more or less a connected dots routine. So supervised learning systems are essentially exposed to copious amounts of labeled data. So that's a very important term here, it's the labeled or annotated data. So for example, images of handwritten figures annotated to indicate which number they correspond to. So we're looking at the example here in the top left, we see a picture of apples. So say all images of apples corresponds to, say, for example, the number 1, and all images of oranges, say, correspond to the number 2. And let's say, for argument's sake, we want some sort of algorithm to sort or load these images into folder 1 or folder 2. So the idea is that after being exposed to sufficient examples, the supervised learning system will begin to recognize the images and be able to distinguish them automatically. So after sufficient training, the system will be able to provide the targets or predictions for the new image or the unknown image that it receives. So if a machine saw a green image, for example, it may well assume that it's looking at an apple and put it into folder 1. So in essence, supervised learning methods are information-driven modeling to create estimation models. These have, I suppose, a myriad of applications such as risk management or risk assessment. So it can be used to determine if, say, for example, if an individual is likely to default on a loan, or determine if a patient perhaps is in a medical environment is at risk of developing a medical complication. Can be used for personalized interactions to determine, I suppose, what content to show a person based on their current behavior or intent, such as like they're using Netflix streaming devices. Companies, I suppose, from consumer point of view, companies are better than ever at understanding why customers buy their products, use their services, or engage their expertise. So machine learning or algorithm, or we can point the machine at a lake of consumer data to detect patterns or preferred channels for consumption. So it can use historical or real-time data to determine that, say, for example, don't like coffee or whatever, and then based on, I suppose, where I shop or where I buy my coffee or how much I buy, can obviously recommend other, I suppose, complement products or coupons, for example, to reimburse, for example. So it won't, however, independently create a new interaction channel that doesn't already exist. So these algorithms are very useful in addressing problems that employ learning as part of their operation. So other potential areas include, as I said, customer segmentation. So customer segmentation based on their preferences, history, behavior, or intent to identify the most valuable or most at risk cohorts. So other applications include NLP, as I mentioned earlier on, or speech, voice, text recognition. So identify and even automatically tag people or things within an image, or read an email or text within a document, or enable a system to take corresponding, as well, actions based on verbal commands even. So other fields include such as fraud detection, so examining anomalies within the data set, so one can identify potentially fraudulent activities or frauds before they do any damage at all. So rather than reactive and seeing like undesirable transaction within your account, you can take preemptive action and stop that before it ever happens at all. So in today's presentation, we won't go into the mathematics underpinning all these supervised machine learning algorithms that exist. But so what this presentation will cover, we'll give some, I suppose, notes or some pointers on the more popular methodologies or algorithms that exist today. So on the bottom left there, you can see the main or more popular algorithms in this field would be Bayes statistics, random forest or RF, decision tree, regression analysis, support vector machines such as SVM, support vector regression and neural networks. So these are the more popular types of algorithms, or your kind of go-to, I suppose, tools or algorithms within the toolbox if you wanted to address something whereby you had a problem with a lot of annotated data available to you. So counter, I suppose, to supervised learning, we have unsupervised learning. So this machine algorithm studies data to identify patterns as well. So however, in this case, there is no answer key. There's no labeled data provided. The machine has to determine correlations and relationships by parsing or looking at the available data. So unsupervised learning is modeled on how, I suppose, humans naturally observe the world, drawing inferences, I suppose, and groupings with like things based on unconstrained observations and using their own intuition. So we can see on the top left there, we can see our robot trying to sort out the apples and the bananas. Okay, so in this unsupervised approach, we wouldn't have informed the machine that they are apples and bananas. But over time, it will, like you or I, it'll figure out that there are two distinct groupings. So as our experience grows, or in this case, that of the machine, the amount of data that is exposed to grows, our intuition or observations change and we become more and more refined. Like you may, I suppose, ask where we can use this or what type of problems are this suited. So there are times when you don't want to exactly predict an outcome. You just want to perform a segmentation or clustering, and the unsupervised machine learning algorithm is used for that. So it's good for exploring the structure of information, extracting kind of maybe say insights that you mightn't necessarily intuitively see, detecting patterns and implementing this into, I suppose, within this operation to increase predictor performance or increase efficiency for a particular outcome. So in other words, unsupervised machine learning attempts to describe the information applied to it by sifting through it and making sense of it. So within, I suppose, engineering, for an example, it can be used to detect unexpected events. So in 2007, we saw the sudden collapse of a bridge in Minneapolis. In 2016, we saw the sudden collapse of a bridge in Milan. So unsupervised methodologies are well placed at identifying non-standard behaviors for a particular item. So obviously bridge collapses and not you hope that it's not a standard, I suppose, situation or example. Also can be used for detect, say, for concrete spalling or crack damage, detect within bridges or high-rise buildings. You can be using sensors to collect data. And then by using sensors to collect data, you can facilitate remote vision problems or vibration-based condition monitoring of a bridge infrastructure. And it can be used to overcome the limitations that are often applied with visual inspections, as many of these only occur every 1 to 5 or even 1 to 6 years. Thus, maintenance can be scheduled now using real-time health data for a bridge or railway lines, for example. So unsupervised methods are also useful in identifying potential systems operation anomalies. For example, Tower Bridge in London in 2020 had an unexpected fault of one of its lever arms and it was left open for a period of time. So these algorithms can be used in predicting the compression strength also of recycled concrete. So rather than having a rubber stamp seal of approval from a particular, I suppose, batch of concrete, this can be used to take various data samples and predict what type of strength it would have. Again, I suppose we won't go into the mathematics of the algorithms, but on the bottom left and there, you can see, I suppose, the most popular algorithms within this type of field. So we have affinity analysis, self-organization maps, K nearest neighbor, or KNN as it's sometimes referred to, and hierarchical clustering. So I suppose to pause and go back to basics, machine learning is particularly suited to problems where I suppose applicable associations, the rules might be intuitive, but are not necessarily codified or described by simple logical rules. Potential outputs or actions are defined by which action to take as depend on the diverse conditions which cannot be predicted or uniquely identified, I suppose, on before events. Also, I suppose it's useful, I suppose, for where accuracy is more important than interpretations or interpretability, and where data is problematic for, I suppose, traditional analytic techniques. So specifically, I suppose, why data, or I suppose data sets with a large number of data points or attributes in every set record, as opposed to a number of records and highly correlated data. Data with similarly or closely related values can present problems for traditional analytics methods as well. And this one methodology can overcome a lot of those problems. So next, I suppose, we have the blend of the two, I suppose, the best of both worlds, so to speak. So it's semi-supervised learning. So this is used to, I suppose, address similar problems as supervised learning. However, in semi-supervised learning, the machine is provided, as I said, some data with the answer identified, i.e. some labeled data, along with additional data that is not labeled with the answer. So in other words, some of the input data is tagged with the desired output or the answer, while the remainder is untagged. So semi-supervised learning is used when you don't have enough labeled data to produce an accurate model, and you don't have the ability or resources to get more labeled data. So you can use this semi-supervised technique to increase the size of your model training data set. So in these cases, the provided inputs and outputs, i.e. the data that you do have, provided the general pattern, and the machine can then extrapolate from this and apply to the remaining data. So today, these algorithms find use, I suppose, in applications pertaining to image recognition and classification. So it's useful to group pictures based on their content and identify like objects in images, identifying images, videos, or text that may be potentially offensive. So it can be used for speech recognition, so understand what someone is saying, or to detect tone and emotion, so seen in developments of modern day chatbots and personal assistant devices, so Alexa and Siri. And can be also used, I suppose, in website page classification. So semi-supervised learning can be utilized to catalog websites based on a variety of criteria, for example, identify potentially offensive content or particular web pages that you mightn't agree with. So as you can see, the applications of machine learning, or ML, within today's environment is rather broad. And the idea of this presentation is that you can see the potential that it has to augment and safeguard many areas across various disciplines. So in reinforced learning, the machine is provided a set of allowed actions, rules, and potential end states. In other words, the rules of the game are defined, and by applying the rules, exploring different actions and observations are supposed resulting from reactions, the machine learns to exploit the rules to create a desired outcome. I suppose, thus determining what series of actions in what circumstances will lead to an optimal or optimized result. So reinforced learning is equivalent often, I suppose, is often described as being equivalent to teaching a child or someone to play a new game. So the idea is that the rules and the objectives are clearly defined. However, the outcome of any single game depends on the judgment of that player, who must adjust his or her approach in response to, the incumbent environment, skill, or an actions of a given opponent. So try and make it a bit more tangible, I suppose, in engineering terms. I suppose these algorithms find use in cost overrun prevention and improvement, or addressing job shortages. Additionally, they find use in optimization resources, by the optimizing car, truck, and plane deployments and routing to maximize efficiency and minimize overall cost for a particular transport fleet. Reinforced methods can also be used in GPS navigation systems to identify the most optimal route from A to B based on current traffic, weather, and other driving conditions. So I suppose, again, to make it that bit more tangible, because I suppose it is the categorization that I suppose be probably least, I suppose, intuitive from most of our point of views. So taking our navigation point from the previous slide a bit further, consider the use of machine learning to reduce traffic congestion when teaching kids. For example, we are in effect using positive reinforcement, i.e. if they don't do a good job, or if they do a good job, you give them some sort of reward, and if they do a bad job, then you don't give them the reward. So this is the same idea behind when we're applying reinforced algorithms to optimize traffic flows and traffic signals. If the algorithm is doing a good job because cars are saving time at intersections, for example, we give the algorithm some sort of reward. If it does a bad job, cars get congested, for example, the reward will go down. So for this setting, the reward could be that cars take a shorter time to get to their destination. So this is something that is hard to directly quantify, because it obviously takes consideration things like your speed, number of traffic signals you go through. However, the goal here, I suppose, in its purest form, is to optimize a resource. That's what we want to get to at the end of the day. And the resource in this case could be, for example, the road surface. And consequently, if we're able to minimize the use of road surface, we can perhaps potentially reduce the need for additional roads. So I hope that you have a clear picture of the four main types of machine learning algorithms and how they could potentially be applied to the world of, I suppose, the everyday problems in the engineering, for example. And I suppose this slide acts as a recap, I suppose, to provide a brief summary of what we've discussed now. So for supervised learning, I suppose, you supervised, unsupervised, semi-supervised, and reinforced learning machine learning algorithms. So this presentation, as I said, we will also touch on some the applications of these. For example, even, I suppose, on how we use these, I suppose, algorithms, some of our own in-house problems, and how we use them to, I suppose, solve these problems. So for the next few slides, I want to discuss with you some of the more applied aspects of AI machine learning. So this particular slide, we have a schematic of our Bosco project, our battery optimization system controller project. So this depicts the microgrid testbed located alongside the Nimbus Research Center on the MTU campus. You can see it comprises a 10 kilowatt PV array, 10 kilowatt BYD lithium ion battery, 10 kilowatt Aquin salt battery and electrical load bank, and 10 kilowatt electrical load bank along with associated inverter units. So this project centered on the development of a retrofittable energy management platform with multi-objective or dual optimization functionality. So it's capable of simultaneously considering multiple, I suppose, expected PV power output, energy storage devices, and the opportunity to supply the grid, as well as zone system load demand to deliver an overall optimal schedule for each asset. So the idea is that it's designed to offset peak load tariffs and supply energy at an optimal cost to commercial, agricultural, and domestic end users. So it's also designed to consider real-time pricing structure and to enable end users to engage in the integrated single electricity market pricing mechanism. That's the day-ahead price forecasting structure that's available now in Ireland since October 2018. So this project harnesses meteorological data, including temperature and solar radiance data, and applied this to a machine learning algorithm in order to derive predictions of the expected power output from a PV array for the next 24-hour period. Additionally, machine learning methods were utilized to forecast the expected system load demands, and then the day-ahead hourly prices or euro per megawatt hour tariffs for the day-ahead were obtained also from the power exchange from the CMOPX platform operated by EirGrid. So now that we're in a position whereby we know the hourly prices, the hourly loads, the demand, the expected PV power output, we're obviously in a position now to employ machine learning to optimally schedule the discharge of the battery system in order to maximize the contribution that our renewable energy generating assets make to the overall energy mix. So this also opens up the opportunity for us to engage in other activities such as load shifting and peer-to-peer energy trading, and an area that is obviously receiving more and more growing interest. So here we present a project with Miker, who engaged with Nimbus to develop a genetic algorithm or GA-based algorithm to deliver a pump schedule optimizer for the optimal extraction of inflow water to dewater a quarry. So here we are very much adopting the sense that what gets measured gets managed. So if you can't measure it, generally speaking, it's very hard to manage it. So I suppose you might ask yourselves why the need for an optimal pumping schedule in a quarry. Well, quarries in level areas with shallow groundwater, deep excavations which are located close to the surface water, often have engineering problems with drainage. Generally speaking, the water is removed by pumping while the quarry is operational. As the quarry becomes deeper, penetrating the natural water table, water inflows generally increase, and it invariably becomes more expensive to lift the water higher during removal. So this can often become the limiting factor in how deep a quarry goes or how deep we can excavate. Thus, one of the key components required for an efficient quarry dewater system to facilitate deep mining activities is an accurate model of the groundwater flow. This is almost a prerequisite, I suppose, in developing any reliable dewatering management system or management model. So for this project, the optimal dewatering system was determined through the combined use of simulation, AI, and machine learning optimization techniques. Groundwater flow modeling and optimization methodologies were jointly employed to determine the optimal cost of pumping in order to reduce the groundwater table of a confined aquifer at steady state conditions. So this concerned the development of a weather forecast module number one, in particular, obviously the direct precipitation element and the resulting infiltration rates into the quarry itself. This was then merged with an energy price forecasting module, as I mentioned earlier. And as I said, real-time pricing was introduced in October 2018. And currently many end users operate a fixed time use tariff structure. And this basically lacks the means of this. I suppose this project enables them to hedge against those price peaks within, I suppose, the uncertain RTP market. So this slide presents another project that we engaged with Miker, I suppose, and they engaged with the development of an AI solution for a water utility company in Cork. So this particular project uses machine learning and methodology to develop an optimization engine to produce an optimal pump schedule to maintain water reservoir levels at Carrs Hill and Straws Hill in Cork. So the operation constraints here require that we operate within a limited level margin, thus ensuring security of supply whilst minimizing energy costs. So this was particularly prevalent during the period of drought experienced within Ireland the past 2 summers. So here's an example from the project's real-time GUI detailing the expected pump schedule. So you can see what when to turn on and off the pumps, or when the algorithm has told us when to turn off or on and off the pumps in order to reduce the overall cost of pumping. And we can also see the expected or the predicted operational water levels. So we want to make sure that tanks maintain the water level within certain upper and lower limits. So I touched earlier on the electricity price forecaster. So this slide depicts, I suppose, a snapshot of the energy prices for 2015, 2016 respectively. So for anyone, I suppose, in any way involved or concerned with the energy market in Ireland, attracts one of the most volatile data sets within Europe. So step 4, the short-term electricity price forecast project, was a 3-year project funded by Enterprise Ireland. And this initially covered, I suppose, the single electricity market architecture in Ireland. It's now obsolete and being migrated over to the ISIN market, or the integrated single electricity market, which better aligns ourselves with the European market and the power exchange hubs within Europe. So this project explored the use of machine learning algorithms to predict the unit electricity price with an ever-extending prediction time horizon. So the premise being that the greater the prediction time horizon, we can facilitate or enable us to better capitalize on the opportunities of load shifting or engaging, I suppose, better or more attractive propositions such as peer-to-peer trading. So here's an example from the project's real-time GUI detailing predicted unit price. And we can also observe in real time some of the data feeds that the model would have used, such as aggregated wind, daily load, predicted volumes. So here, this slide presents a project with Ambisense. So now an environmental analytics company with offices in Dublin, UK and Netherlands. They engaged Nimbus to develop an AI platform for anomaly detection within their sensor data streams. So Ambisense are now transforming, I suppose, how environmental risks are assessed and managed through the use of advanced data science and methodologies. So this slide presents a sample of the data from pump pressure sensor readings, atmospheric pressure measurements, and recorded battery performance metrics. From this data, we can develop AI algorithms to detect anomalies within the data as shown. So this is an example of some of the data, I suppose, anomalies within the data that we would have detected. So MDCL, so this is a startup based in Blanchardstown, Dublin, comprising Declan Lee, Sean McMahon, and Dr. Thomas Ahern, a consultant physician and endocrinologist in Louth Hospital Group. And they teamed up with Nimbus to develop a healthcare professionals to tackle diabetes. So Nimbus as a tech gateway facilitates an environment, I suppose, where endocrinology, technology, and business development can coexist to realize their individual potential as a unit. So diabetic retinopathy is the leading cause of blindness in the working age population of the developed world. So the condition is estimated to affect over 93 million people worldwide. The need for a comprehensive and automated method of diabetic retinopathy screening has long been recognized, and previous efforts have made good progress using image classification, pattern recognition, and machine learning. So with photos of the eyes as input, the goal of this research is to create a new model, ideally resulting in realistic clinical potential. So for this project, all images are taken of different people using different cameras of different sizes and pertain to the pre-processing section. This data is extremely noisy and requires multiple pre-processing steps to get all images to a usable format for training a model. Furthermore, the variance between images of eyes is extremely high. For example, figure 1 above shows us images with no retinopathy denoted class 0, while figure 2 depicts examples of other ends of the scale class 4 prolific retinopathy. So with current COVID situations, both Dr. Thomas Ahern's availability to this project limited. Thus, this is actually an ongoing project with Nimbus that revolves around the development of AI vision platforms to diagnose diabetic retinopathy using deep learning. So over the past decade or so, another interesting or popular research area in artificial science is sentiment analysis, or SA, is emerging. So SA, or opinion mining, refers to the use of natural language processing, or NLP, text mining, computation linguistics to methodologically recognize, educate, and evaluate and examine emotional states and subjective information. So the main computational steps in this process are to determine the polarity or the sentiment of a tweet. So the sentiment is ordinarily categorized into a 2-tier, i.e. positive or negative, and then 3-tier could be positive, neutral, or negative classification structure. In general terms, I suppose sentiment analysis is a way of identifying and categorizing the polarity of a given text, which can be done at document, sentiment, or phrase level. So for example, social media messages like tweets have been polled to analyze user satisfaction of product, I suppose quality or service that could be useful for subject emotional state analysis. So this summarizes a sentiment analysis project commissioned by PredictView as part of a larger project containing, I suppose, examining the field of multimodal classification for sentiment analysis. So PredictView uses AI to track and identify, I suppose, indicators of depression, substance abuse, and other concerning sentiments within social media contents in a timely manner. And the next speaker, Randy Waters, will go into this in much more detail than I will. So next, I suppose, in terms of our concluding slides, I suppose to get you thinking about, I suppose, machine learning in a kind of different context. So it's often asked, why can't anyone explain how a machine reaches conclusion, or can we trust machine learning algorithm? So this is part of the mystery behind machine learning. So unlike traditional statistical models, the models created by machine learning algorithms are extremely complex. While there is a method to the madness, it is not immediately obvious or linear. So the exact path through a neural network, for example, is not easy to trace or to observe in hindsight. So thousands or even billions of rules or parameters can define a model. So as a result, the exact internal processing or pathways that go on within a neural network are a bit of a black box, even to the data scientists that actually created it. So the more important question is the algorithm or method being applied appropriately to the problem at hand, or the one that we're looking at? So if the analytic mechanisms, or more specifically the logical progressing pathway or rules, are not clear or easily reproducible, then how do you validate the results, you might ask? So it's very important that we don't confuse it all black box processing with blind faith. So when it comes to machine learning, the validation of an algorithm is really simple. So when tested against new data or unknown data, for example, we just ask ourselves two basic questions. Does the algorithm actually predict future events or result in a desired outcome? And can you put the output into some sort of action? I suppose that's it in its essence, or in a nutshell, so to speak. No more, no less, really. So the validation criteria for machine learning algorithms are kind of simple, really. So on the other hand, the process of selecting which algorithm to use, auditing and tuning an algorithm to deliver these results is the opposite. It's very complex and anything but simple. Numerous factors must be accounted for, such as what algorithm or algorithms, because if you're using a hybrid approach, best suit the problem or data at hand. What data elements, aka features or inputs, should be included? Can the data be cleansed, transformed, or refined to better expose key elements to the model? So it's often referred to as feature extraction engineering. And is there any data pre-processing in mind required? So how should the algorithm's parameters, for example, be configured or tuned for optimal performance? So the model must also, I suppose, be cross-validated and audited to avoid artificial engineering, I suppose, a deceptively accurate response, for example, overfitting. And admittedly, I suppose, simplistic example is it is relatively easy to create a model that predicts yesterday's weather with a high degree of accuracy, but that same model may not predict tomorrow's weather as good, or be the only model that works. So ultimately, developing, I suppose, a functional machine learning system is an iterative and, I suppose, intense process that is, I suppose, part art and a lot of science. And so I think that's it. I hope you found it some way interesting, and I'll pass you on to Manuel, or the next speaker, and I can take any questions at the end. Thanks very much.
Thank you very much, Connor. Very interesting presentation. And now we're going to move on to our next speaker, Randy Waters. Hi, Randy. How are you doing there?
Manuel, how you doing?
Not too bad. So
yeah.
While you are getting ready, I'm going to introduce you to our audience. That's okay?
Okay.
Perfect. So Randy Waters brings over 30 years of entrepreneurship, technical innovation, software engineering, product, and operation executive leadership. Most recently, he served as the CTO for Fast Model Technologies, a sports technology company based in Chicago. Randy also directed development of large-scale switching and network system at Alcatel and at Bell Laboratories. Randy has a Master and Bachelor of Science degrees in Electrical Engineering from the University of Oklahoma and holds 2 technology patents. Did I miss something?
Sounds good. Thanks.
When you're ready.
Yes. Can you see my screen or my presentation?
Yes, I can.
Okay, perfect. Okay, well, thank you, and I'll get started. So hello, everybody. PredictView Technologies is a digital health and AI technology company that uses predictive intelligence to detect behavioral health issues. We work with Dr. Lynch and the team there at Nimbus to help build our solution, and we'll talk about that a little bit later. Let's start with what is PredictView. It is an artificial intelligence depression alert system for at-risk employees and veterans who express depressive behavior online. We are providing the mental health care industry a way to proactively detect mental illness for people who haven't already taken the initiative to ask for help, and perhaps before a catastrophe happens. This is also a source of valuable information for therapists while treating their patients. Okay, the effects of depression and anxiety is $1 trillion cost to the global economy. And also, very sadly, 22 US military veterans take their own lives every day. This was all pre-COVID. Early research reports that as many as 83% of US employees are experiencing mental health issues coping with the upheaval of the last several months. Similar results are expected for Western Europe and other regions around the globe. The direct impacts are lost productivity due to absenteeism, presenteeism, direct medical costs shared by employers, and suicide. Afflicted employees have five times more absent days than other employees. They're 5 times more likely to be on disability. They have 4 times higher overall medical costs and are 2 times more likely to quit or be fired. The conservative cost to replace an employee is $15,000, and in many cases much higher. There are additional indirect costs due to how these employees affect other groups and other employees and business processes. Ignoring the problem or terminating afflicted employees is just no longer an option. It's just too costly. So as a result, more and more companies are investing in mental wellness programs to reduce this hit to their bottom lines. Billions of dollars are being invested into technology companies that digitally treat mental illness. There are dozens of companies offering solutions ranging from huge networks of mental health care professionals for immediate on-demand teletherapy. Think of Uber ride shares for the mental health industry, and AI bots that converse with people. However, nobody is using written online expressions to detect signs of mental illness. So let's talk a little bit about detection. There are written daily journal apps for users that are feeling depressed or have anxiety. These are AI bots that provide responses and suggestions based on the information provided by the user. There are other daily speech diary apps. Some use AI to determine changes in speech patterns to detect stress, anxiety, and depression. Dr. Lynch talked about that a little bit earlier. Some even use AI to simulate a conversation with a therapist. These are very useful applications that are mostly focused on self-care and mindfulness for their users, but they do require a person to recognize that they are troubled and will be proactive in getting help for themselves. Few of these solutions are tied to licensed medical healthcare therapists that analyze the results and proactively engage these users for professional treatment. Online expression is an invaluable source for detecting behavioral illnesses. Social networking sites, professional networking sites, these are all great sources for detection. Some researchers believe this is the primary source for detection and is currently untapped. Dr. Becky Inkster, a neuroscientist with the Department of Psychiatry at Cambridge, argues that data from social networking sites should become a high priority for psychiatric research and mental health care delivery. So the solution is a detection service that employers can provide as part of mental wellness programs offered to their employees. This opt-in digital detection service inherently complements treatment solutions that provide on-demand teletherapy, as well as other AI bot solutions that we spoke about. Most importantly, the detected information is only provided to mental health care professionals that are authorized by the employee. Employers, bosses, colleagues, even family members are not privy to this information. This information is protected like all other private personal medical data. Data privacy and security are critical platform functions that will comply with personal identification information, HIPAA, and other state GDPR type regulations. Long term, we see this detection service being delivered more broadly through the healthcare insurance providers. Starting with the corporate enterprise market is a great way for us to establish market traction and to validate the technology while evolving it. Psychiatrists are interested in this kind of detection service to gain insights into what their patients are thinking and feeling outside of their therapy sessions. So a little bit about the product that we call Predictive Intelligence is an AI software as a service platform that detects signs of depression and substance abuse. We call these signals. We will provide this as a mental health care wellness benefit to companies for their employees and to veteran organizations for their veteran members so that there is necessary trust for opt-in. We are doing this through mental health technology partners that already provide mental wellness treatment solutions. We simply add on and provide a detection feature for their application. The platform is built to instantly detect signs from millions of employees and veterans. Minutes can sometimes matter for intervention and hours can matter for treatment. The platform is built to easily adapt to additional behavioral issues, geographies, demographics, languages and dialects, age groups, cultural mannerisms, etc. It is compliant with personal identification information, HIPAA, and all the regulations that we spoke of. We conducted a trial with a social media monitoring company for school districts around the US last year. A high school student posted an end-of-life message on her Twitter account. The trial customer's existing solution, which uses keyword searching software combined with many, many human analysts, missed the subtly worded suicide signal. Our platform flagged it and immediately, and the monitoring company notified school officials who contacted her parents, and the potential suicide was averted. We were very happy about this. As it turned out, minutes mattered in this case. Had we been an hour later, apparently we would have been too late. A little bit on how this thing works. The platform is built on a streaming data pipeline implemented on a public cloud, currently using Google's GCP. It is architected for massive scalability. The first stage ingests data from online communication platforms like social networking sites and professional networking sites like Facebook, Instagram, Twitter, so forth. The pre-processing stage separates the posted message into its components: text, emoji, image, video, audio, and determines what classifications apply to the customer's subscription level. The classify stage is where the AI models reside. This is what we worked with the Nimbus team. We have built several behavioral classification models that include depression and substance abuse. The message components are sent to every subscribed classification model to determine the confidence probability of that classification. A value above a set threshold constitutes what we call a signal. The results are then sent to the trend analysis stage where that determines if there are deviations from a person's historical pattern that are large enough to produce a signal. The results stage designates the message or historical trends as a signal or not. The notify stage then alerts the platform's analyst of a signal via the user application. We are positioning this product for licensed and trained therapists to function as these analysts. So that's what we want. We want people, doctors, and other trained healthcare professionals, mental health care professionals, to be looking at these signals. The action stage is where the analyst decides what to do about the signal. The analyst may decide that the signal produced is not worth acting upon and therefore dismisses it. Otherwise, the analyst will promote the signal to a ticket and assign some kind of workflow action to be taken by a designated therapist. It could be assigned, for example, to a psychologist with geographic or demographic proximity, or someone trained to deal with substance abuse. That person then takes whatever protocol action is prescribed by the organization. The results of the action stage are ultimately fed back to the AI models for further training and learning. This is important. The models use supervised learning, as Dr. Lynch described. It took a lot of cost and effort to create the data sets to teach the models to detect depression and substance abuse. We had to curate thousands of examples of what is a depressive message and examples of messages that are not depressive to create models that were useful in real-world applications. We had to differentiate between a depressive message and a message about depression. Feeding hundreds of thousands of messages that have been assessed by trained and educated mental health professionals back into the models is the ideal method to teach the models. They will get very smart very quickly at those kinds of volumes. The platform learns from these decisions its users make on a per account basis. So this is beneficial so that the AI models can become tuned to how the specific account organization views the signals generated. Okay, a little bit about Nimbus. Nimbus is our primary research partner. The talent team there, working with Dr. Lynch, developed custom deep learning neural net models for natural language processing that we use. They developed data set methodologies for behavioral health issues. They developed machine learning model training, validation, and test methodologies. And they are currently developing joint representation for text, images, emojis, audio, and video. An example of this is you want to be able to look at, let's say, a message that has text and image. 70% of social networking site messages have both. And what you want to do is be able to look at the context of both the text and the image to understand the context of the actual message. One example is a tweet that we saw, and the text and the caption simply said, "This is me," and the image showed a person laying in a street that floodwaters were passing over their head. And if you just looked at the text, "This is me," you wouldn't conclude much. And if you only looked at the pictures, you wouldn't necessarily conclude much. But you put the two together, and it's very descriptive of someone obviously feeling flooded and depressed. Finally, a little bit about the company. PredictView Technologies was spun out of a sports technology company called Fast Model Sports. It originally started as a product for university athletic departments to help them cope with behavioral illness issues with their student athletes, their coaches, and their recruits. Over 2 years of development and over $2 million of funding have already been invested to develop the working system that is deployed. And we are currently raising capital to take this product to market and generate revenue later this year. Okay, Manuel, that's it for me.
Thank you, Randy. Very interesting presentation. Thank you very much. And now it's time for the Q&A, for question and answers. Now you can use the chat if you want to ask any question to one of our speakers. We can wait maybe 1 minute to see if someone wants to ask something. Okay, if there's no questions, then just to conclude, I would like to thank all our speakers and contributors. Thank you very much. And thank you to you as well for watching and for attending this workshop at Beyond IoT. And I hope you have enjoyed as much as I did. So see you next time. Thank you.
Thank you.
Thanks, everyone. Thanks, Manuel.